Okay, so we are talking about the regular expression, and in the last class we have seen the how this regular expression is corresponding to a epsilon NFA. So, given a regular expression, we can construct epsilon NFA, there exists epsilon NFA such that the language accepted by that epsilon NFA is the same as the language accepted by the regular expression. That means, regular expression and the epsilon NFA are equivalent. Now, today we will talk about the equivalency between the DFA and the regular expression. That means, given a DFA, we have a language which is accepting by that DFA. Now, corresponding to that language, we can construct a regular expression whose language is the same as the language of the DFA. So, let us write this in a theorem. So, if L is a regular language, which is basically L, if L is accepted by a DFA, then L is denoted by a regular expression. Okay. So, this is the statement of the theorem. So, given a L which is accepting by a DFA, that means, there is a DFA M Q0 F such that this L is nothing but the language of this DFA. Then we can prove that, I mean we can construct a regular expression R such that whose language is same as this L. So, that means, the DFA and the regular expressions are equivalent. So, given the DFA, we can construct a regular expression which is accepting the same language. The language corresponding to the regular expression is same as the language of the automata. Okay. So, we have to prove this. So, to prove this, we take a DFA, and DFA we know it is a finite state machine. So, the state space is DFA is finite, state space of DFA is finite. Okay. So, yeah, let M is a DFA which is having this tuple Q0, or this we can start with Q1 because I will explain, and F. So, this is a Q is a finite number of states. And sigma is a finite number of alphabet, and this is the delta is the rule. We know delta is nothing but the transition rule, and Q1 is the starting state. We take Q1 because we want to. So, because this state is finite. So, without any loss of generality, we can assume the states are Q1, Q2, Qn if the cardinality of Q is n. Suppose there are n states, n could be anything. Then we can rename the states. There is no nothing. There is no harm of renaming the state. So, that state we are renaming at starting from Q1 to Qn. We could do it from Q0, but anyway it will help us to prove this theorem. So, our states are numbered by Q1 to Qn. Even we can do it 1 to n, states are 1 to n, 1 means Q1, 2 means Q2, like that. Okay. So, states are numbered by 1 to n, Q1 to Qn, and Q1 is we are taking as a starting state, and F is a subset of this subset of this. So, F is also some consist of sum of this q i's, which is the accepting state or the final state. So, this we can assume, I mean by renaming the states we can take this by this numbering. Okay. Now, this is our state space, this is our state space, this q, and now we define some notation which is denoting by R I j k. So, now q is, let us write this, q is q 1, q 2, q n. Okay. Now, we denote this R I j k. This is basically the set of all string. We are at q I, set of all string which is starting from q I and which is ending to q j. This is q I to q j. Okay. And what is this k means? So, that means it will visit some state by this rule delta. So, this is say q q I 1, q I 2, this is say a 1, a 2, something like that, or a I 1 in general, or a 1, a 2, a 1, a 2, like this. So, q I 3, a 3, dot dot dot, some number say q I L, which is basically our this, then we go to q j. So, these are the intermediate states, direct arc, these are the intermediate states coming from the this rule delta. So, that means delta of q I comma a 1 is q I 1, like this. Okay. Delta of q I 1 comma a 2 is q I 2, like this. So, this way we go. So, this is the, and now what is this k means? K means the number, this I 1, I 2, these are the states we are visiting in the intermediate path. So, this number has to be less than k. So, that is the restriction. So, this number has to be less than k or less than equal to k. So, this all this I 1, I 2, I L has to be less than equal to k. We know they are greater than. So, this is the restriction. So, this consists of set of all string x. So, x is nothing but a 1, a 2, a L, then a L plus 1. So, this is set of all string which is starting with the state q I, this is I, and at the end of the string it is reaching to the state q j, and the intermediate, these are all intermediate state, and the intermediate state, the number which we are seeing is strictly less than equal to k. So, that means intermediate we are not seeing any state which is more than k. That is the restriction, that is the meaning of this, and there is no restriction on I and j with k, I j could be greater than k. Only thing, the intermediate node we have a restriction, there is no restriction on I and j. Okay. So, let us write this in a form like this. So, this is the set of all string such that delta hat, because this is a string, delta hat of q I comma x is equal to q j, and so we are starting from q I, and with this x we are reaching to q j at the end of the string, and all the intermediate nodes has to be labeled less than equal to k. All the intermediate states, states are nodes, states are labeled by a number less than equal to numbers less than equal to k. This is the symbol Rijk. So, we are starting with ith state Qi, we are reaching to jth state, but in the intermediate state we are not visiting any node which is more than number more than k. So, that is the this. Now, if k we put n, so what do you mean by Rij n? Rij n means we are starting with, this is the set of all string, we are starting with Qi, with x we will go to Qj, and the intermediate node we are not seeing any node which is more than label more than n, but there is no node which is label more than n. So, this is the set of all string, there is no restriction, set of all string, we start with Qi which can reach us to Qj, that is all. So, that is the meaning of this. Okay. So, if we put n, then it will come, this part will not come, because n is all the states are less than equal to n. Okay. So, this is our notation Rij k. Now, we will try to get a recurrence on this notation, recurrence relations, and then we will have a regular expression for this language. Okay. So, let us just write the. So, we have a recursive relationship on Rij. So, this we can define. So, we have to prove this. This is our claim. We can define Rijk recursively by this relation Rijk is equal to Rij k minus 1, this is one case, union of Rik k minus 1, Rkk k minus 1, this is star, and Rkj k minus 1. Okay. This is our recursive relation for this Rij k. We have to prove this. This is our claim. This is our claim. We have to prove this. Okay. Okay. So, yeah. So, that means what? This means what? This means we are starting from Qi. This is the set of all strings starting from Qi. We have to go to Qj. Now, there are two possibilities. One is, and in the intermediate path, we do not want to see any node which is labeled greater than k. We are only allowed those nodes, those states whose label are greater than less than equal to k. So, there are two possibilities. One is there will be no node of label by k. So, one path is like this, all the nodes will be less than k. All the nodes we are visiting over here are less than k. So, we have to take all those such string which is starting from here going to here, and which is not seeing any node which is equal to k. So, So, that means we are seeing only the nodes which are less than strictly less than k. So, that collection of the string denoted by this. Okay. Less than k means less than equal to k minus 1. So, this is the set of all string r I j k minus 1. So, we are starting from q I, we are going to q j with those strings which are not seeing any node which is k. So, that is this way, this is one possibility, and another possibility is we have a node which is labeled by k. So, q k is there. So, if q k is there, then we can go to q k, and from this q k we can go here. Okay. And there are few possibilities here also, sub possibilities, that there may be only one q k in this path, or there may be many q k's in this path. So, if there is only one q k in this path, then there is no no q k here. So, this will be denoted by all the nodes are strictly greater than k, all the nodes are strictly less than k, strictly less than k. So, this will be denoted by r I k k minus 1, and this will be denoted by r I r k j k minus 1. So, concatenation of these two, if there is only one q k in this path. So, this will be denoted by this without appearance this. This star means it may come, may not come. Okay. In that case, this is this concatenate with this. Now, if there is more q k's in that path, then what will happen? If there is more q k's in this path, then we can just have this q k's like this. So, suppose this is the first q k, then this is the second q k like this. There may be two or more q k like this, q k like this, then we have. So, there is no q k over here. So, these are all less than k, there is no q k over here, less than k, less than k, less than k. Okay. Now, this is the path r I k k minus 1, and this is the path what? This is the path r k k k minus 1, because there is no q k in this path. This is also r k k k minus 1, but this is a loop. So, that is why we have put in a star. So, it may, so this is our x 1, this is x 2, and this this is our x, this is our y, and this y may repeat, y star, y concatenate with y, some another y, but that y is coming from this, because there is no q k in this path, there is no q k in this path like this. So, that will eventually give us this star. Star means it star involves zeros also. So, zeros means no appearance, that is the case where only one q k present. If there is 2 q k, then we have this one. If there is 3 q k, we have 2, 3, 4 like this. So, this is the star concatenation of this. So, this is the informal proof of this. This is, if there are two ways, one is the string like all the path is having no node which is labeled by k. We have a path with node labeled by k, but that may come 1 time, 2 times, 3 times. So, that is why we have putting this. So, this is the proof of this. Okay. Okay. So, we will take this, and this is true for all I and j. So, this result is true for all I j from 1 to n and all k. So, k can be 0 here for all k. So, what is the meaning of k 0? What is r I j 0? Rij0 means set of all strings. So, we are at Qi, we have to go to Qj, and the intermediate node the intermediate node we will see must be labeled less than equal to 0, but our states are all labeled by Q1 to Qn. So, there is no states which is Q0. So, that means there is no intermediate node in this path. So, that means the direct path will come, direct arc will come. So, if we have a arc from Qi to Qj, direct edge. So, that means delta of, not delta hat, delta of Qi a is equal to Qj okay. Yeah. So, then this consists of all such AIs, such that delta of Qi a come equal to Qj. This is our Rij. If Rij 0, if I not equal to j, but if I is equal to j, if I is equal to j, then what will happen? That means Rii 0. So, we are at Qi, we want to go to, if there is self loop A, then okay, otherwise it is epsilon. So, it consists of all such A such that delta of Qi A is Qi union of epsilon. This is our Rii. Okay. Now, we will take this result to have a regular expression corresponding to this language. So, that we are going to show now. Okay. So, just to recap what we have. So, we have given a DFA, we can construct a Rij, which is nothing but set of all string such that delta hat Qi comma a is nothing but Qj, and all the intermediate nodes labeled by less than equal to k. Okay. Then we have seen this recurrence. Then what is the then for f, suppose f consists of, these are the state Qi1, Qi2, Qir. Suppose they are the final state of the automata. Then by this notation, what is our f, what is our language? So, then the language is nothing but, so we start with 1, that is a, and we go to any string which can start with 1 and we can reach to one of the final state. This is one final state, and we have no restriction on the intermediate nodes. So, that will give us the set of all possible possibilities which can start with Q1 and which is going to I1. Union of R1 I2 in union of R1 IR. n. So, this is our language. This is the language. This is the language. If this is the all accepting states, then we start from the starting state which is q 1. So, we start from q 1, and any string which is reaching to one of this final state q of I 1. So, this is R 1 I 1 n, because we do not want to put any restriction on the states, we want to visit all the states. So, this is q of I 2 like this. So, this is R of 1 I 2 n like this, we continue. So, this is q of I 3 dot 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 q of I r. So, this is the language. Okay. Now, we are going to, in the next class we will show that this will corresponding to a regular expression. So, we have a regular expression which will accept this, I mean whose language will be corresponding to this. So, that we will discuss in the next class. Thank you.